Let's spend a few minutes discussing halogenation and hydrohalogenation. As we learned from reading the textbook, the stereochemistry in the product is anti. And you might be wondering, how should I know this? Well, scientists did not know this until they ran experiments like the ones shown here. So there's really no way for you to look at these without any other information and predict anti. And scientists, chemists, did not know whether we would get anti or any other stereochemistry until they ran the experiment. So now that we have the experimental results, they analyzed it, came up with the fact that the stereochemistry is anti, and we can then use that to predict the product of similar reactions. And that's kind of the name of the game for all the reactions we've learned about in our textbook. So let's go ahead and draw the product. We know that we're going to react the alkene just like a nucleophile, and as we pointed out in the textbook, in order to get anti-stereochemistry, we need to make the fancy three-membered ring intermediate. And I'm going to put a wedge here to show that I've created a new stereocenter there. I'm sure you'll agree that this is not going to be a new stereocenter. It has two hydrogens attached. It will have two hydrogens attached in the product. But this is a new stereocenter, and so I'm going to indicate that I form both of them because there's no influencing, no driving force that would push me to form just the wedge or just the dash. I'm going to form both in equal amounts. And of course, I lost the chloride as the leaving group, and that's going to be the nucleophile now for this next step. We would expect this chloride to react at the less substituted side, and that gives us a product that looks like this. I'll maintain the wedge here. Here's my newly added chloride, and of course I have both enantiomers of this forming because I had both enantiomers of my intermediate form because I have no stereochemistry on the starting material or on the reactant, nothing to influence the outcome. So we're going to get a mixture of both. And I should say that this is not anti. This is not anti. We're only going to see stereochemistry, the relationship between the two chlorines, I mean, if we have two new stereocenters formed. So let's look at the next problem I have on this page. All I've done is move the alkene from the end to a middle carbon-carbon bond, and we're going to get the same outcome in this case. So we could draw the mechanism. And actually, now that I think about it, I forgot one step here. There are three arrows in this mechanism, of course, because I formed two new carbon-chlorine bonds, and I broke this chlorine-chlorine bond. So this second arrow, be sure that you add that to your notes. That also occurs, and that allows me to make the three-membered ring intermediate. So I'm going to be sure to draw that here. I'm going to draw my skeletal structure the same. I'm going to use wedges because I prefer wedges to dashes, just a personal preference. And of course, you can recognize that I've created two new stereocenters here. I should be able to create the dashed version of this molecule as well, and I'll draw that here just for your records. So these are a pair of enantiomers that I've drawn here. I don't need this plus-minus anymore because I've indicated both of them. And I have, of course, the chloride leaving group, and that can react with either of the two sides of my three-membered ring intermediate. Let's show both and just explore how that might help us get to the product. So I'm going to draw a blue product here with my blue arrows. There's the original chlorine, and because this was an SN2 style backside attack, I would expect the other chlorine to be a dash. And you can see here now we see the anti-stereochemistry because we have two different stereocenters. So let's switch colors and show attack at the other carbon. So there's my original chlorine on the wedge that broke open the three-membered ring. Here's the new chlorine that came in with my green arrow, and you can see again backside attack. That should be a dash. I hope you'll agree with me that these two molecules, the blue one and the green one, are enantiomers. Just for kicks, let's look at that chlorine attacking the other enantiomer that I drew. Again, that's the chlorine that was originally attached. Here's my new chlorine. And I think I have one more color here. Here's the new chlorine. The original chlorine is still attached at a dash. And you can see here that I've come up with a pair of enantiomers as well. And let's compare my two pairs of enantiomers, the blue and green, compared to the green and purple. I'm sorry, the red and purple. Well, I would say that the blue and red are the same molecule, and the green and purple are also the same molecule. So you can see here that I get the same outcome, regardless of if my chlorine attacks this dashed triangular intermediate or this wedged triangular intermediate. So I'm going to cross these out because they are not additional products, they are the same product that I drew before. And these show the anti-stereochemistry. Let's look at a few more examples. Here's one with bromine. We've got an alkene. I'm not going to draw the mechanisms here because they're the same as what were on the previous slide, but you can see that if we put a bromine on each of these carbons, we are going to obtain two new stereocenters. So we need to draw stereochemistry at those stereocenters, and we know that the product is the dibromide. We know that it's anti. And I can draw the other enantiomer here because, again, there's no control over which enantiomer would form in a preferentially. So I'm going to draw both of them. I'm going to make sure that I still show the anti-stereochemistry on these two molecules. Let's look at this molecule. I've just moved the alkene into the chain instead of the ring. This will be a new stereocenter. It'll have an H and a bromine, a small carbon chain, and a large ring attached to it. But this, I don't think, will be a stereocenter because it has a symmetrical ring attached to it. So let's go ahead and draw that. So there's my new stereocenter. There's my other bromine that was added. There is no stereocenter there, so we can't observe that these bromines were added in a anti-fashion, but they still were. We just don't have evidence for that because of the stereochemistry of the product. And of course, we would obtain the other enantiomer of this product. And so we still get an anti-addition. We just can't observe that because this carbon is not a stereocenter. So there's no way to observe that that bromine was added anti. This is in contrast to the example up here where we've created two new stereocenters. We can easily observe that those bromines were added anti. Let's make things a little more exciting here, and add water to our chlorine and our alkene. So this is the same alkene and same chlorine I started with at the beginning of this video. The only difference is now we're doing this in the presence of water, so we're going to expect a slightly different outcome. So the intermediate will look the same. I'm not going to draw the arrows for you. And I have a chlorine, and in this case I also have water. Now, when we have this setup here with chlorine and water added, it's safe to assume that there's a lot of water present, and so there's going to be one chloride for each chloronium intermediate, but there's going to be a lot of water. And so the water actually will outcompete as the nucleophile. And because this is a weak nucleophile, we're going to add that to the more substituted side, and I'll explain that in a second. So here's the intermediate that we're going to produce. There's no stereochemistry on the end carbon, so I'm not going to put a wedge there. I will put a dash for my water, and I'm going to make the other enantiomer, which I won't draw here because it's going to take too much room. And now I have one more step here because, of course, my nucleophile was neutral. I need to do a final proton transfer step, and I'm going to use another molecule of water to grab the extra hydrogen to make my neutral product. Of course, the other enantiomer forms as well. And I added the nucleophile to the more substituted carbon. And we can understand this if we think about these two carbons that bear the chlorine as having partial positive charges because they have a positively charged chlorine attached to them. And so I'm going to draw partial positive charges there. I'm going to try to draw them in a suggestive fashion so that we recognize that there should be a larger partial positive charge on this carbon because it is more substituted. So this carbon will be more stable with the partial positive charge, so there should be more of the partial positive charge here versus right here. And that's what attracts our neutral nucleophile. The larger partial positive will be on the more substituted carbon, and so then the water will attack at the more substituted side. And that's going to be true for any of these hydrohalogenation reactions. Let's look at this second reaction here. We can look at this and say, well, this is a more substituted carbon than this one, so the chlorine will form a triangular intermediate with the alkene. The water should add to this side, and if I add chlorine here and OH here, I should come up with two new stereocenters. So I should show that the product is anti. So I don't need to draw the mechanism. It's going to be the same as what you saw previously. So if I put a wedged chlorine here, I need to have a dashed OH group. And then, of course, I have the methyl that was left over from our starting material. And I can draw the enantiomer of this as well. I could draw a dashed chlorine here, OH on the wedge, and then the original methyl group is also on a dash. And so I have anti-relationship here. That's the stereochemical relationship. I have OH on the more substituted carbon. That's the regiochemical outcome, regiochemistry. So we have regiochemistry here, the OH goes on the more substituted carbon, and we have stereochemistry here, the OH and the Cl are anti, just like we saw with halogenation.